Today we're going to start one of my favorite topics, which is finding volume by rotation. All right. So we go from a two-dimensional curve to talking about a three-dimensional volume. So what we're doing is we're taking an area under the curve or relative to the horizontal axis, and we're going to rotate it around 360 degrees, and that's going to create three-dimensional solids for us. We're going to cut those solids into pieces, and each cross section will be a circle, and we're going to use the integral to add all those circles together and get the volume of the shape. So what I want to do first is just show you how that solid's created. So if we're looking at the integral from 0 to 4, this green piece here, that's telling me the area under the curve here. I wish that was shaded in, but it's not. So that's telling me that area under the curve here when I think about the integral from 0 to 4. Now, when we take that curve and we rotate it, right, look at what happens. So I've now got it rotated, so I've got the mirror image on the bottom because all I've done is I've taken this curve and rotated it, right? But it also forms these circular cross sections because if you imagine this as the radius, as I rotate it, it's going to be coming out of the screen towards us, maintaining that same distance, all right, all the way around. That's why we have the mirror image on the bottom, because when we think about it two-dimensionally, we've got the diameter happening there, right? But this curve actually comes out of the screen towards us, almost like a clock hand, and then rotates to the bottom, its lowest point, and then rotates like into the screen, if you can imagine that, back to the starting position. So we end up with a solid that starts here at 0, ending at 4, but is this kind of cone shape. All right. So that's what we're going to be looking at today. We're going to be able to do this relative to the y-axis, the x-axis, and curves that are not part of either axis. All right. I mean lines. So I could do it around the line -10, for instance. So we're going to look at each of these contexts today. But that's kind of the visual of what's happening. What we're going to do now is switch from this visual to a problem, and we're going to use that problem to draw conclusions about how we actually find that volume. All right, so we've got the function f of x equals square root x, here. All right, and we're going to find the volume formed by rotating this solid about the x-axis. So, and we're looking at the interval 1 to 4. So when we rotate that, it's going to create the mirror image relative to the axis of rotation. And once again, that's because when we rotate it, it's preserving this distance here. All right. So now if I make a value showing that rotation, I've got a circle here, and I've got a circle here, formed by that rotation. All right. So the circle center at 4 is at 0. That's the axis I'm rotating around, correct? So let's go ahead and take that cross section and think about it. So I've got my center at 0, and then my radius is that height of the function there, right? So my r is equal to square root x. We know that area of the circle is equal to pi times the radius squared, right? So we've got infinitely many circles in here, circular cross sections, if we're thinking about them being like wafer thin. Like as they get infinitely thin, we've got like an infinite number of these circles just stacked on top of each other. All right. So since we have this stack of circular cross sections, right, we can use the integral then to get to the volume, because if we do the integral of area with respect to dx, right? We've got the area of the cross section, and then you can think of dx as multiplying times the number of cross sections we've got here, right? So it's like the width in some regard, all right? So this is like telling us it's adding in the third dimension. So we're getting from that area of the cross section to the height or the width, right? It's accounting for that interval for us. So when we do this integral, then we're going to be doing the integral of pi r squared, right? I was a little sloppy here. This should say ax, right? dx and rx. All right, so we have to identify what our radius is, and then we're going to take that value, that function, square it, and we can use that to figure out what our volume is, because we're stacking those disks on top of each other. So our equation, when we've just got one function and we're rotating it about the x-axis, is this. So let's follow through this example to its finish. We're looking at, I should add my bounds here. Let's not be sloppy. My bounds are 4 and 1. And then I've got square root x squared dx. So I'm looking at the integral of x from 4 to 1 times pi. So I've got x squared over 2 times pi from 4 to 1. So 4 squared over 2 minus 1 squared over 2, whole thing times pi. So I've got 16 over 2 minus 1 over 2, or 15 halves, times pi, and that's my volume for that rotated figure. All right, so let's generalize then and give ourselves something to work with. Well, when we're rotating a curve, we're going to have two situations that we talk about. We're going to have vertical and horizontal rotation. All right, and when we're rotating, we're creating a solid. So if we're rotating it, all right, vertically, or I should say with vertical cross sections, all right, so we're thinking about rotation that happens this direction, right? Well, let's give ourselves some reference here. That happens in this direction. We are going to be talking about with respect to x. So our equations will be in terms of x, all right? And we're always going to do our interval a to b, all right? Volume equals our interval a to b. We've got pi on the outside times r of x, all right? And then we're going to be subtracting our axis of rotation from that, minus our axis of rotation squared dx. So we'll see what that axis of rotation means right now. So if I'm talking about rotating about the x-axis, my axis of rotation would be y equals 0. If I'm instead, so let's say we had this, right? When we rotate about the, about the x-axis, we'd get circular cross sections like that. Let's say instead, I had that function, right? But I was rotating about a different axis. So I was rotating about y equals -1, right? So if I'm rotating about that, it's no longer going to be just attached at that corner, it's going to be that distance away, right? So this distance is -1. So it's going to be 1 away, and then the mirror image. So we've got a slightly different shape we're talking about here. So to account for that distance of 1, we need to subtract the axis of rotation. So this integral would be, let's say this is f of x equal to x. Right? This would be our function f of x, or what that correlates to, our radius, minus our axis of rotation squared dx. This one accounts for that additional 1 there by doing minus negative that axis of rotation -1. So now our radius is 1 larger, right? Because it's 1 below the x-axis. So that's what it means when it says minus the axis of rotation. So that's when we have one curve. What about when we have two curves? Well, when we have two curves, it's going to be just like when we were talking about the area. So this is one curve, right? Where we had the upper and the lower, right? We're going to have something kind of similar right now. So what we have instead is outer and inner. So we're still going to be using the same idea to calculate our integral. So we've got pi times our interval a to b. And we're going to have our radius minus our axis of rotation squared. But now we've got another function. So we've got two of them going on. All right, thinking about this, instead of upper and lower, we're going to think about outer and inner for our functions. So inner is going to be closer to our axis of rotation, and outer is going to be further from our axis of rotation. All right, this all seems like a lot, I'm sure. All right, but it's the same idea when we're talking about with horizontal cross sections, except now we're talking in terms of y. All right, so our one curve now we're talking about c to d because we're talking about y values instead of x values. Still minus our axis of rotation squared, and we're doing it with respect to y. And then two curves is the same. All right, so volume equals pi times our interval c to d, and we've got our outer squared minus our inner. Oh, sorry, this should be a y here, and this should be a y. So same idea as when we're working with area, right? These ones you're going to have r of y means we're talking about some expression where we've got r of y means we like solve for x, right? So this is going to be solved for x in terms of y. What does this type of rotation look like? Well, if we've got this function, the rotation is now happening this way. So our cross sections are horizontal. Right? And this would be like saying x is equal to y. Right? So when I write it as x equals, that's the same as saying our function with respect to y. And that's what you'd be using for these. So go ahead and give the problems that follow a try, and I'll be dropping into your breakout room to help you out.